Hello everyone. So in this short video, I believe um, we are going to um, first to find the moment generating function of exponential distribution, and then mm, after that we are aiming to find the distribution of um, y, which is equal Xbar, and we need to find what's the distribution of y using the moment generating function. So let's start by using the moment generating function for the exponential distribution. So let's say it's mx of t, and this equal expectation e to the power tx, and because this one is integral, then we just take 0 to infinity, because this the exponential is just continuous random variable. So that will be e to tx f of x dx. Now we write the from 0 to infinity, rewrite it again, e to tx, and we have theta e to minus theta x dx, and we can write this as the following. So 0 to infinity theta e to minus x, and we've got theta minus t dx. So now we write it again. So 0 to infinity theta e to minus x, and it's t minus, sorry, and it's theta minus t dx. And as we know from that, when this integral is with respect to x, so we've got in the exponent we have theta minus t, we have minus, so we need to theta here, we need to multiply that by theta minus t times minus 1, so that will be like that. So it will be minus theta, and then we need to divide that by theta minus t, and then the integral 0 to infinity theta minus t, and then e to minus x theta minus t dx. Put negative here, so all of that will go with the integral. So we've got minus theta in the numerator, and then theta minus t in the denominator, and the integral for this one will be minus e to minus x, sorry, so it will be e to minus x theta minus t, infinity and 0, and this one will be minus theta and theta minus t, and this one will be e to minus infinity minus e to 0, e to minus infinity, that is equal 0, and then e to 0 equal 1, so will be theta divided by theta minus t, and this is the moment generating function of exponential distribution. So mx of t equal theta divided by theta minus t, and we can simplify this again by divided by theta, the numerator and denominator. So theta divided by theta minus t divided by theta, so that will be 1 in the numerator, and then 1 minus 1 over t theta, and we can write it like 1 minus 1 over t theta to the minus 1. Then we can conduct from that x is also gamma distribution with shape parameter, which is 1, and the scale parameter, which is, this one is 1, so this one is 1 over theta t, and then 1 over theta t to the minus 1 to the power minus 1. So that will be x is gamma distribution with shape parameter 1, and the scale parameter is 1 over theta. And we can find, for example, expectation of x, which is equal 1 times 1 theta, which is equal 1 theta, and the variance of x equal will be 1 variance of x will equal 1 over theta squared. Now we are going now to find the moment generating function. Before that, we should just say y is equal x bar. Then we can write x bar as 1 over n, x1 plus x2 plus xn, and all these x's are independent. All are independent. So we can write my of t as the same before, which is expectation e to t y, which is integral 0 to infinity e to ty, and then we can write that as f of x dx. We can write this as expectation e to t, and then we can just write 1 over n, x1 plus x2 plus xn, and then because they are all independent, all x's are independent here, So we can write that expectation e to t x1 divided by n times expectation t x2 divided by n, and then up to expectation of e to t xn divided by n. Then my of t, so that will be m x1 of t divided by n times m x2 t divided by n, then up to m xn t divided by n. Now we've got the moment generating function of exponential, so we just need to we need just to change, instead of t we just put t over n, so that means 1 minus 1 over theta and then t will be t divided by n to the minus 1, and the same thing in here, 1 minus t divided by n theta minus 1, for x2, and then up to xn the same thing, 1 minus t divided by n theta to the minus 1. And because they have the same base, so and they multiply each other, then we just need to say 1 minus 1 over n theta t to the minus n, because we multiply them n times. So that will be my of t, the moment generating function of y, and then variable y, which is y equal x bar. So that means y, we can conduct from this moment generating function that y is gamma with shape parameter here n, and the scale parameter will be 1 over n theta. So can say the expectation of y, so that equal n times 1 over n theta, so n with n and cancel out, then it will be 1 over theta. This is the expectation of y. Now the variance of y, can say the variance of y, so that equal n times 1 over n theta squared, so that equal n times 1 over n squared theta squared. Can say this squared go with that one, n cancel out, so the variance will be 1 over n theta squared. So that's the variance of y, or we can say this is the variance of x bar. We can say if we can justify that by using, let's say, expectation of x bar, and we have expectation of 1 over n sum of xi, so that will give me n divided by n expectation of x, so the expectation of x equal 1 theta, and we've got the expectation of x bar equal 1 theta, and we found that in the previous page that variance of the expectation of x bar equal 1 theta, and the variance of x bar which is equal 1, which is equal to variance 1 over n sum of xi 1 to n. So we can say 1 over n squared variance of sum of xi, and we know that variance of sum of xi, we know that variance of sum of xi is equal to sum variance of xi. So that means we've got 1 over n squared times sum variance of xi 1 to n. So that will be 1 over n squared times n, and the variance of x is 1 over theta squared. So n with the n, the denominator cancel out, so that will be 1 over n theta squared, and that is the variance of x bar. So that matches what we found using the moment generating function. We've got the variance of x bar equal 1 over n theta squared. I hope you enjoy the video. Good luck and thanks for watching.